Okay, hello everyone. Welcome to a Wolfram Language Design Review. This is an early part of our big cycle of design reviews for version 14.3. And today's design review is about the compiler. So I think that I'm excited to see the third item here about generators, but let's start off with the first item.
Fine. Okay, right. So this is about compiler information. No new symbols or anything, just new functionality. So compiler information gives information about types and functions. And right, so one of the things that we found was that if you ask for, say, compiler information on a function that's popular, like create type instance, there are a lot of them, and we wanted a way to select them out. And the way we decided was to put, and this actually works quite nicely, as you put typed with a pattern for the type that the function has. And so this here selects all the versions of create type instance that return a C array. So it's actually super useful. So it
Okay,
helps.
but that pattern representation of types, meta types, I don't even know in type theory, what would that be? That patterned type, is that a parameterized type? What is that?
Well, we have parameterized type. This is matching on the sort of expression representation, the expression language, rather than the sort of type theory language. So this is matching on the sort of full form. So the type that you would enter for one of these C array things would be something that looks a bit like that. It might have for all type in there, but it's going to focus in on this thing here.
No, but what I'm asking, in type theory, is there an analogy to this, patterned type?
Well, you have type variables. I mean, in
That's not the same
pure,
thing. I mean,
pure.
this is a family of types. There are many types consistent with that symbolic pattern, correct?
Yes, yes, yes. And we have I mean, in pure type theory, it would be a lambda. The type itself would be a lambda expression with lambda variables that would represent, things to be bound, bound or unbound.
Although that's a little bit different, isn't it? I mean, it's kind of um
But we don't want to make, I mean, this is using
I'm
our
just trying to
nice
understand that this
pattern
syntax.
language,
What's
right?
that?
It's using our nice pattern
Well,
language
I
and
know that. I know that. I'm just trying to understand whether there's a more general use of that. For example, let's say you declare something. Could you declare it to be a pattern type?
Well,
we,
so
right,
there's for all type, right? I
yes,
think right. So
like this,
yes, the
yeah.
analogous way that you would do stuff like this, you know, in like a function declaration is with for all type. We've talked at various points about like supporting a more patterny syntax for all type. But there's some things that make it kind of difficult. Um, right. There's sort of notation that you sort of need to have in for all type that there isn't really a good way of expressing with patterns.
Right.
Okay, fair enough. I guess that's really the answer then. I mean, it might be worth looking at that at some point. I'd like to understand what
We
the.
look at this every so often, and there's similarities and differences. Yes.
Okay,
So
but this is a meta type that is different from a for all type.
correct. Yes. This is like an expression selector, like you might put in match queue
No,
or
but it
something.
is a type. It's a sort of meta type, isn't it?
It's a way of selecting a whole family
All right, but anyway,
types.
it's a way of basically selecting out the things. I don't really quite understand this. Why are all those things? Oh, I see. They're all the for alls. This is getting inside the for all.
Yes, this goes inside the for all. You can put a for all here as well, if that would be possible as well. So, but
All right, but anyway, this is just a way of selecting. Now that we are beginning to have a huge number of type signatures, you know,
yes,
uh, polymorphic functions. then this is a way of selecting down.
Drilling down to find them, right? Because you
Looks
know
fine to
that
me.
there are things that work with zeros. So is this? I think this
Looks fine to me. Looks just
good.
fine.
Okay, good. Right. So next thing. So this is a new symbol. So this would be current compiler function, which you put inside a compiled function, and it sort of binds to specific details about the function in which it appears. So let's just see what that means. So I compile this function here, and I'm printing, excuse me, doing a print of the current compiler function. And so when I run this, I get this compiler function sort of expression, and it shows the type of the function. So this function is going from like an integer to a packed array of integers, and it doesn't have a name. Now this is
So
particularly
naively, if I were to say in ordinary execution of an ordinary expression, if I were to print something, print the head on from the stack, would I get a similar kind of thing?
no, because you'd get an expression stack, and we don't really have a notion of functions, you see. So,
Right.
excuse me, right. So
Yeah.
for better or for worse, in the evaluator stack, it's just every level of the expression. Now, some of them might be functions or set delayed functions or excuse me, other things. I'll just show a couple more
Yeah,
examples
okay.
and start. So here I'm using information on the current compiler function to get the type. And so that prints out. Oh, and we've spiffed up the printing of types everywhere to make sure they use our nice, type specifier syntax. And in particular, it's incredibly useful to get the return type. So this is for writing polymorphic functions, you want to get the return type of a function. And so we've had a sort of internal way of doing that, but the idea is this is the sort of canonical way of doing that. Now, there's actually a compiler function type and a compiler function object that's coming back. And here I'm returning, so I'm generating the current compiler function, and I'm casting it to an inert expression and returning it. Now, I can't return the compiler function itself because that would lead to a sort of cycle, an infinite type. So a function can't return its own type. But here, so the type is, and this is just showing what the return value is. And I haven't hooked up, but there should be some sort of properties of this thing, a little bit like we have, say, like compiler environments.
So let me ask a naive question. Okay, in the evaluator, so you've got a function, and current compiler function is attempting to return essentially the head. I mean, it's like hash
Well,
zero, isn't it?
yeah, it's a little like hash. There's right, except it knows a lot more than hash
Right.
zero does.
Right.
And the whole point of it is that the reason you use this is to get that meta information that hash zero
Right.
doesn't have.
Right. Right.
And where does the meta, because current compiler function is
when the thing is compiled. So here's another example. I mean, they get a little bit more hairy, but here I've got a function declaration in an auxiliary function, and then and it's actually written polymorphically. So here I'm compiling it, and now it knows the name of the function, and it's pretty useful to be able to get the name of the function. I would imagine, maybe not this version, but we could actually have a whole stack, like when we have these error messages, it has like this quite useful call stack. This is doing the same thing for runtime errors, and you can see the stack of things that you reached. Now I'm using the same declaration, okay, auxiliary function in another thing, but now the type, you see here, the type was integer goes to integer, and now the type is packed array of integer goes to, is a packed array type. So this could be used to give more useful error messages, but in particular, this is the thing we really want to solve. So it's very common that we want a function that returns, for example, a 0 of a particular type. And we've had a sort of hacky way of doing it, but this is now, so we do a type hint of the return type. And so now we get, for example, this function is returning an integer 8, or this function is returning an unsigned integer 16. So this is super useful. I mean, we really need to have a documented official way to do this. And this is
But it's worth noting, by the way, in that one case, you can also just write typed of 0, integer 8, and so on. Right.
Yes, you could do
in this
that.
particular case.
But I want to have an abstraction. Yes, that's correct. But I want to have, sometimes you don't quite know, or it might be, it might be type of, for example, or there might be something a bit more involved, and these things are quite,
Why is type hint? Why do we not provide the the courtesy of just saying 0? The type hint could have a second argument that is called function return type. So it just does this. The type hint does that.
Well, I think there are other times that you'd want to. Okay, there's a few things. Like, for example, sometimes you might want to cast, a list of things with the type return type,
right.
Or or you don't always want it inside of type hint.
Right.
Or you want it in a cost, for example. Are you saying you want it in a cost?
Yep.
Right. Or
Yep.
put it in the
There's a
variable.
whole bunch of them. So this is probably, this isn't going to work, but you might have a more complicated type computation. But exactly that. It's not just type hint, it's like cast. There's a family of
All right, fair enough. But this idiom, information of current compiler function return type, seems like it should just be given a name.
Well, we did the name, which we called it compile backtick return type. In fact, it exists. So we had a thing like that.
Well, but I'm just saying, you probably given.
Well,
that's the thing you
say.
I mean,
certainly right. The quote return type could go inside the current compiler function. Probably, it doesn't necessarily have to be an information on the outside.
Right. So hang on. What are you saying? I'm getting confused.
Current compiler function could have. I don't know what the arguments of current compiler function are. But they could be a property argument that includes,
Oh, you're saying to have something like this?
Yes, I'm not sure that's quite right. And I mean, this current compiler function is kind of weird because what it's doing is it's taking the thing that it's in, and it is essentially taking #0, but it's taking the compiled #0. Is that correct?
But it could be like, say, current value tells you about where the value of certain things where you are, but it's not quite like current value.
Yeah, I don't know. I don't think the analogy to #0 is great. I mean, like, first of all, right, it's a little bit like something like stack, but most of the things, maybe even all the things in the current compiler function are known at compile time, not at runtime, like all this type stuff and the name of the function and so on. And then also, right now it only goes one level, but we did talk about, presumably you can have a version of this that does the whole stack.
Yes, absolutely. It'd be super useful.
Can this be macro replaced, lexically replaced at compile time?
I don't even know. I don't know what you mean by macro replaced, but it is dealt with at compile time.
It's dealt with at compile time, correct?
So it's. Okay.
Like when you ask for the return type, that obviously is that's known at compile time.
Yes,
and it can only compile the cast because it can resolve that at compile time.
I see. It's part of what is compiled, and the fact that you can print it out.
That's just a fancy feature.
Yeah, because we have. Let's see. There we go. Right. Well, okay, so this is the code that actually gets, so it's just turned into an integer 8. So
Right, let me understand this. By the way, why is it called compiler function? Function compile, what is compiler function? What is you showed
Well,
before the symbolic thing compiler function. I'm not sure I've seen that before.
no, that's they go together. So the this and this.
Yeah, but what is okay?
yeah.
Function compile returns what? A compiled code function,
It
right?
returns a compiled code function like we see here.
Okay, so what the heck is a compiler function if it isn't a compiled code function?
Well,
Right. So that's I don't I also think it's a kind of questionable name. So compiler function is just it's just what gets returned by current compiler function. So it's metadata about the function. It's
actually, it's
not
the
actually a function, right?
serialization. It's the expression serialization of the compiler function type, more technically. So, but we could use a different name.
We should use a different name because compiled code function. I was very confused there because compiled code function is a function that is a compiled code function. Compiler function, you're saying, is actually just the type of the compiled function. Is that correct?
It's with other things like the name of the function and the call stack and everything.
And how is that different from, I mean, what do you
Right.
mean the
It's
call stack? Well, that's a runtime thing. Isn't this compiler function thing determined at compile time?
Correct. Yes.
So it
well,
can't have a,
actually,
yeah,
I guess it doesn't. I'm not sure all of it has to be like these things like return type and function name. Those are determined at compile time. I'm not sure necessarily every part of it has to be determined at compile time. For example, if we supported some, well, yeah,
stack. Then it
No,
would,
I
yeah,
think
for
it
some
would
stack
be.
information.
I think there always would. Well, if it was recursive, that's complicated.
all right,
Right.
but
So,
this
but
is,
the,
go
the
ahead.
way to think about this compiler function object though is it's like the same thing as like information data, the thing that gets returned by if you run information of plot and it
Right,
returns that box has head information data.
right,
That's basically what this is.
Why don't we
right.
call it, why don't we use information data for it?
I think we actually talked about that. I don't
We-
remember what the
it's a bit different. Um, I mean, this could be, yeah. I mean, it relates to the current function. It's a sort of marking point in the current function. Um,
I mean it could be information data. I mean,
that yeah, that would have a lot of tentacles. And information data has a very precise way of working that this is not quite.
I thought
Right.
information data was just an association. I don't really know, but I thought it was just
But we experimented with that, and
Why couldn't this actually just return an association? And then you just sample,
it could return an association. I
and
think at
then you
one
just say
time
of return type or something if you want to. In other words,
it
right.
could return an association.
Well,
I
I
think
guess
one
I mean,
time,
one thing is the compiler doesn't really support associations like that very well.
but it's in the serialization, so it probably could. Let's just look at one of these.
Okay, so you're saying we would have, compiler, what is it? Current compiler function would return something with type, I don't know, compiler function or compiler
Yeah,
function
yes.
information or something, and then that would get serialized as an association.
Look, you see, there is an association in compiler function data. There is an association in there. I mean, we could just return this association.
well, I'm just thinking about okay, what is the correct name for current compiler function, which right now is an unbelievably confusing name? What is it really? It is
Well,
at this stage,
it's in this function return sort of meta information about the
right.
state
So,
of the
so for example, naive
compiler.
things like dollar input tells you what file you're currently reading from. There
Yeah.
isn't, stack open close. How do you get the top of the stack? What's the name for the top of the stack? What's the name for the head of the function that you're in?
Well, I think it's just don't think it has a. I don't think it has a. I
It's
mean,
just
it's
probably last of stack, right?
like fast.
Yeah.
Yeah.
It's a little less trivial than that in general, because you might be already deeper in the stack when you call it.
Right.
Oh, I see. Deeper relative to the head.
Yeah.
So
So it's
what are some other
sorry.
analogies of, you're inside a thing and you're picking up its head? Where do we have that? Are there things in graphics where you're inside a thing and you're picking up the head? Because that's what this is effectively doing, right? This is saying, well, no, you're picking up.
Well, I guess it's
Oh.
also kind of lexical, unlike stack, because
It's
it's
more like option value expansion, you know?
Oh yeah, that's a good example. Yeah.
Which, by the way, is semi-lexical because it happens lexically, but at this stage when the function just starts executing.
Yeah.
Okay, but so what this is doing is it's giving you information about the current function, which happens to have been compiled. But if it
Yes.
wasn't compiled, I mean, if it wasn't compiled, this thing could just say it takes n expressions and returns an expression.
It could say something like that.
But and that function could be polymorphic. So is that correct? So it could have yeah. That's just
Well, no. By the time current compiler function's returning, it must have resolved to a concrete
Yeah,
type.
there'll be a concrete type. It'll never return a polymorphic.
So in other words, even though the function definition might be polymorphic, this is returning at a particular call, so it has
Right.
Exactly.
resolved.
Yes.
Actually,
Yes.
I guess it might be a nice bonus feature that it could return what polymorphic type this concrete type was sort of derived from, if you know what I mean. But
Yeah.
that would be a bonus thing.
Yeah. That sort of thing would be useful. I mean,
Okay.
it could return the name of the file it was defined in and the line number.
Yeah, it could have all kinds of stuff.
All
So
kinds of
what is
stuff.
it? It is I
Well,
mean, it's
most
almost
of the time, it's tied to the declaration that it appears in. But I guess the only time it doesn't is if you use it inside of like a anonymous, inside of a pure function.
Right.
How about current compiled function information?
That would be up there with one of the longest symbol names.
Yes.
Right. You see, the only problem with that is it's closer. So I don't want to be difficult, but it's closer to this thing here, and it's not quite the same as that. Current compiled function data. It's not quite the same as this.
What do you mean it's not quite the same? It's not quite the same because it's metadata, right?
Well, this is like one thing. There might be many functions nested inside of this. This is a function with respect to the Wolfram language, to the Wolfram language interpreter.
Yes.
But we're talking about things that are, compiled functions with respect sort of to the, compiled code type of thing that we have.
What?
I mean, to the...
if I apply a compiled code function to the argument 3, it's potentially going to do something. Is that what you're saying?
Well, what I'm saying is it's something that lives in the Wolfram language expression ecosystem. That's what I'm saying. And we're talking
and where does this other thing live?
Well, it's inside compiled code.
Well, it's like typehint, for example, which evaporates outside of compiled code. Is that what you're saying? This doesn't evaporate.
Evaporation might be more complicated than typehint.
Right. I don't think it would evaporate. No. So.
Well, I mean, it might do something. I mean, it might, like, I don't know. I mean, certainly it can't tell you what the return type is going to be.
Unless it just says expression.
Unless it just says express. I mean, okay, but it can't tell you the input types because that's going to be a list and it doesn't know how long it's going to be.
Right.
But I mean, it could do something kind of, it could, if we decide this thing serializes to an association, then it could return an empty association or association with very little in it or something, which might be kind of weird, but it wouldn't explode.
Okay, but basically, I'm still trying to wrap my head around what this thing really is.
Right.
At
Um,
execution time, this is essentially type another information about the function you are currently in. Maybe one day it could be 3 levels up from the function you're in.
Yes. Yes.
The function you're currently in, and I mean, you are, if I might say so, executing the hack of inventing this compiler function in order to have a thing to return from this, which you are then going to take apart anyway. See what I'm saying? I mean, the compiler function itself is never independently useful. Is that a true statement? It's only its subparts that are useful.
Right. You mean the object that gets returned by current compiler function?
Correct, yes.
You could say that about information. It's only the individual information elements that are useful.
No. I mean, information has a default useful. I mean, maybe this does too. I mean, maybe printing this.
Yeah.
Okay.
Yeah, I mean, I think that would be the. I think primarily, right. Right. I think most of the time you don't really care about returning the whole big object.
Exactly.
And most of the time you just care about one thing.
Yes.
Okay.
um,
Okay.
I have an impression, Stephen, that what you're talking about now, it seems like this compiler information function, current compiler function, acts more like a hidden slot, like #0, than like a standalone independent thing, because the slots they only make sense inside the function.
It's a good point.
Is it like supplied, where you
Yeah, I
get
mean
things from the
something like
environment?
that. Yeah, something like that.
I don't think it's.
Supply doesn't exist yet.
Yeah.
I mean, there's probably a preliminary documentation page for it.
Yeah.
Mm. I mean, okay, hold on. That's a good point, that the hash, both hash and supplied, are creatures of where they are used, so to speak. They don't exist outside of their use. I mean, same with stack. I mean, what the heck is this thing, really? Does it actually have anything to do with the compiler, really? I mean, other than it can be resolved by the compiler.
I mean, it basically
does.
can only exist in the compiler.
Right. It knows about compiler specific, details like stacks and types and names. And it's useful for using it to build tooling based upon it. That's really what we want something like
Right.
this for.
But most of the information in it is deeply compiler specific.
Yes, I think that's true. Yes.
What about something like current compiler data?
Could be.
Can you
Well,
write that one down?
Data is a little vague though.
current compiler data.
Current compiler. It's not state because it isn't state. It looks out. It sees what it's, what house it's living in, so to speak. It's not its state itself. Could you just type in current compiler data? But
Absolutely. Like that. So we would have things like this.
current compiler data of return type. And get rid of the information.
Yeah, fine.
I mean, I don't think we want to call it. I don't know. I don't love that. Current compiler something seems reasonable. Um,
Oh.
Introspection. I mean, is that that's not really even the word either, is it? Is it it's not really introspection because it's outro. It's going out. There will be a lowercase d.
Right. We don't really use metadata anywhere, I don't think.
We
So
do in import, but
we
it's not
do.
widely used.
But that's specific to like XML and
No,
things.
no, it's not. It's for
Oh,
types
yeah.
that have a metadata. But
Meta information.
Yeah.
That information is also
Oh,
used in
yeah.
like images and stuff like that. It's used
oh
as an
yeah, I'm
option.
sorry. I'm wrong. Yes,
Right.
I don't think metadata is right there.
No, I don't either.
I don't think state is right. I don't think metadata is right. Okay, so what else is there around those things?
I wonder how bad it is that we're losing the word function because we are talking about return types and things like that. If we exclude it from the name.
It is very much tied to the function, not, if you call it something like state or metadata, you might wonder if I have a function and then I say f of current compiler metadata, will that return the same thing as if it's not inside the f? And the answer is yes, because it's tied to the outer function. But yeah.
I mean,
what about current function types or current function type data?
It doesn't just return type data.
Yeah, it's not. Yeah, it's more than current function data.
Then we're going to go back to current compiled function data.
It's a bit long, but it's not too bad.
It's feasible.
And open close would then return what? If you didn't give a return type there, what would it then return?
Oh, then it would return a compiled function data type with the sort of stuff in it, a little bit like it does now. So there'd be a compiled function data type, and that would serialize to an association. So
I guess we could. It could be equal. It could be the same as all there.
yeah. So that's all, and then a bunch of other things and open close. Current compiler function.
Compiled function data.
Sorry.
Current compiled function data.
What am I talking about? Current compiled function data, like this thing here. Right.
Yeah.
Okay.
I think this is okay. Unless you have another great idea.
I'm struggling, and we've talked about this a bit. Fine. Okay.
I don't love the fact that data is not usually very dynamic for us. Or is it?
By what do you mean by dynamic?
Well, I mean, data is usually something like, country data or something, which changes.
Oh.
Right? As opposed to something which is right in the middle of a computation.
Not necessarily just that, because there is also evaluation data, which is much closer to.
That's a good point. That's a good point. This is close to that. And by the way, should have a C also to that, probably.
Yeah.
Okay. This looks good. Let's move on.
Good. Right. Let's messing. Sorry, I was just taking a few notes. And right now, okay, here's the generators. Right. So now we've been through various incantations of this, and this is right. So let's just come and have a look at this. So generator, so the idea here is you mark a function. So I have a function here, but it's marked up as being a generator. So when I compile it, it's going to return like a function that returns a generator. So it's a data structure, and then I can call sort of, method. So there's two yields. So it's yielding two things, and when I call the last one, it's reached the end. Okay, so that's generators.
Let me try to understand what the heck this is doing.
Yes, fine.
Okay. What is it? Is yield like produce as opposed to yield like a yield sign on a road? Is yield
It's
like
produce.
you are giving something?
It's like produce.
Okay. I have to say I consider that very confusing because, at least I can't even remember, in the old world, do they have yield signs in the old world? They certainly have them all over the new world.
Yeah, I think so. Yeah.
But Stephen, there is some sense to that as well in terms of the yield signs, because basically every time when you call yield, you return the evaluation control because the function gets frozen and it returns
That's what I
evaluation
thought was the usual meaning of yield in these
Yeah.
settings.
So it's kind of both here.
Ouch.
It is like a return. Actually, it really is a return. It's genuinely a return.
So explain to me what this is doing then.
Well, actually, maybe we could. It could be we could actually use the symbol return. That would be a very weird thing to do, but
it would have two returns.
right. But then because the function has been marked as being a generator, that would not do the usual thing.
Well, let's look at
That'd be very odd.
receive. Can we look at receive as well?
No, I want to understand this function here.
Okay,
What the
fine.
heck does this function do?
But receive is kind of related to
Okay,
this.
fine.
So,
Let's
right,
see.
fine. So receive is the other way round. So here I have a generator function, but now the function is frozen until it wakes up. So I send things to it. Okay. So I'm compiling this.
Why do you use print rather than echo?
Oh, fine. Do you want me to use echo?
I don't care.
Right. Okay. Well, I'll do one echo and one print. There we go. Right.
Oh no.
So now this is also doing something which I think is very interesting. It's instantiating code for a data structure, which is something new that we can do now. So right. So here we go. There's the generator. Now, initially it's frozen. Okay, so you have to sort of wake it up with a call to next. Now I'm going to send something to it. So it gets sent, and that is the result of the receive, which gets echoed. And it runs along until it hits the next receive, and then it's frozen again.
Sorry, why'd the receive of 0 again?
Right, that's a default value. So if I used the next on it, that would wake it up, but the return of the receive would be the default value. It's very useful to have that because it also gives a default type for the receive, which otherwise you've no way of knowing what it's going to, what the receive is going to return. So I think that's pretty. It also avoids having to have some complicated type sum that comes back, you see, because if nothing gets sent, look, you see here, I'm going to call next, and it prints.
Okay, can we get to some basics here? Because I'm still still struggling to understand the basics.
I could show you some more examples. I've got.
Do you want to show a more non-trivial example?
Yeah, absolutely. So this,
just so I get what the point is.
Right. This is a bit more non-trivial, I believe. So this is, I've put compiler on. Right. So this one here, there's a loop, and it goes around the loop, and whenever it's divisible by this, so let's compile this. And so I make, every time it's divisible by this argument, it yields that thing. So this is yielding every number that's divisible by 7, you see.
Yeah. I think the really important point, sorry, just a quick comment to understand this.
By 17, right.
The really important point is that normal functions, they execute in their entirety until they hit return or something. Whereas when you have yield, you freeze the function at that point and you return partial result.
What's the difference between sow and reap on this?
Sow and reap doesn't yield, doesn't stop doesn't change control
Right.
flow.
Yes, yes. You don't get the so at the point, right? That it's
What do you mean?
So when you call so, I mean, it doesn't actually change. It just keeps running, right?
Yes.
It's only when the reap returns, which it just does in the normal course of evaluation, that you get everything back. Here, when you hit a yield, it basically throws all the way to the outside of the function, and it returns whatever was yielded. But then it has state. So the next time you go into the function, you then restart where you left off.
Oh,
the
where
last
do we
yield.
preserve the state? So I don't quite
Preserved
understand.
That's this data
internally.
structure.
Oh, that's this gen thing in your
That's
thing
the
here.
data structure. It's a handle
Okay,
to
so this is a mutable object. This gen thing is a mutable
Yes.
object,
yes. So I
like
think
our
that
other data structures.
like our
Yes.
other data structures. Yes.
So it's a mutable object that is maintaining essentially the program counter in some very low level version of it.
No,
in other words,
no, there's only one program counter. I can show you. I know lots about how they're implemented.
no, but
Yeah,
just so I
it
understand,
generates
Yes.
multiple functions. It's super clever. So this
Right, but-
function gets turned into about 3 functions that get called at different stages, you see.
Right. Conceptually, that data structure stores all the state it needs to evaluate this function, and it stores where it last left off.
Right.
which is like the
Absolutely.
program counter, isn't it? I mean, why am I
No, the program. Yeah, I mean, if you modify the program counter, you go to another bit of code.
sure?
Yes, it is closely related to the program counter. If maybe an actual implementation, it is
Not using that, but
But-
why do you say it's a coroutine?
Because a coroutine is a function that can be entered or exited multiple times in one invocation. So it's an example of that's a coroutine, and this is a particular style of coroutine.
Okay, but the main point is you essentially get to run a piece of code, and I mean, I could make this if I made a list which just has a bunch of yields in it. I'd make a list with a bunch of yields. Or maybe you can't do that.
Yeah, you should be able to.
Right. So hang on. You want to do? Let's try and
Make a table of yield of I, comma 10.
right. So we've got that, and you want to have table of like
Get
this.
rid
Why
of
do you
that
need that
module.
module there? Get rid of the module.
Let's get rid of the module like that. But it has to return right.
Why is there a
Could you have it?
semicolon?
Could you have it return the table?
No, it can't. They don't. They only. What happened there? There's some. I'm sure that.
Oh, I think I know that. If you use do, it'll work. But this is kind of stupid. But what is the return type of yield?
It's null. Like the functions. Right. This will work.
Okay, now let me see if I understand here. If you say, wait a minute, you're just saying,
Yeah.
why is there a 10 there? Oh, because it's got the
There's no.
Right. So
right.
first,
Okay.
yeah.
So,
this,
now just
yeah.
do next of next of next of next of next of that. Okay.
Yeah,
So now
it's-
do next again. Okay. All right. Now do the if you do a table of ds of next, comma 15.
Right. So
Okay,
eventually
fine.
you get.
Okay, that's what I expected it would do.
Good. Right.
Okay. So let me try to understand this. Okay. So it's like calling eval effectively. This ds of next is like calling eval for the next round of now evaluate this until you get to the next
result. Yes.
breakpoint.
Yes.
Right. And it's like saying continue until you hit the next yield.
Yeah, right.
Or run off the end or terminate, which is what happened here.
Right. Okay. Okay, so let me understand. So can you show me an application of this?
Yeah, fine. So here's right, here we go. This is flatten. Okay. So we have, and this is kind of an interesting one because this is a generator calling a generator. Okay. So we have a function declaration and it takes an expression, and it's going to return a generator of expressions. So if it's an atom, it yields it. Otherwise, it loops over the elements, but calling flatten on the on the elements. So let's come and get this going. And right. And there we go. Come on, come on, come on. Right, there we go. Right, so I'm going to generate one of these guys. So it's I've got the data structure, and so basically it's going to return, these things one at a time.
I get it.
You see, so it's flattening, or it's walking down through the tree.
Yeah, okay. Yes, I get it. I get it.
Yep. Here's one. So there's quite a bit of code here, but this is merge sort. And
but most of these things, like merge sort, you just want the answer. Why do you want it? Why do you care?
Well, no, so it's part of it is it's returning an iterate, it's returning a generator.
Yes.
So you can if you didn't want the whole thing, then it wouldn't do the whole computation.
Right. There are, of course, if you only wanted 5, the lowest 5, there are algorithms for that.
So how is this related to lazy stuff?
Very.
It's very related to lazy stuff.
Yeah, you can say that it's
very viable way to build lazy stuff with this. But look, you see, I've made a thing like that. See, what's nice is it yields them one at a time. So the first one comes in order.
Yeah, I understand. But so let's say I was generating primes, and I had some piece of code that would run forever generating primes. And what you're saying is you yield at each prime, and then to get the next prime, you can maintain the state.
Yeah, absolutely. It's just totally easy to, all this nasty bookkeeping is done for you, courtesy of the
right. So I mean, another thing would be, I don't know, you're enumerating permutations or something, and there's an easy way to get from one permutation to the next.
Yes. Yes.
Right.
So
by the way, of course, you can have infinite generators as well.
Yes.
I mean,
here's an outer.
Sure, that never end. When you go next, next, never end.
This is a version of outer that applies. This is like an associative outer that yields up. So I spent lots of time on these things, but it is generating. So it generates the results in the same order that outer does, but it does them with a generator, and it's actually quite.
Okay, but the point of this is that you can generate a result, operate on that result, and then just keep going.
Or throw it away. You could say, fine, I finished, sod off.
Yeah, right. But that's right. I understand that. But the most important case is where you're maintaining state in,
yes.
Now
you can always maintain that state yourself. You can always write your own custom data structures and things, but I can guarantee that things like this merge sort algorithm would.
I've needed this a bunch of times, right? So let's say the main case where I've needed it is there's a whole bunch of internal state that's built up, and yet I want to return, and then I want to keep going.
Yeah, well, that's exactly. Yes. That's what this is good for.
Right.
But its compiler has to be compiled. But the compiler can handle expressions. So,
Well, how much? I mean, so practical question for right now.
Yeah.
Do we think this is okay? A couple of things. But right now, this is not going to particularly be an end user. I mean, people could use it, but it's just like, it's another thing on top of the data structure story.
Yes.
So, but what I'd like to ask is, let's say we're using this, okay?
Mm-hmm.
What functions could we now build that we've never been able to have before? Like, for example, could we build something which does, where there's a checkpoint in some, I don't know, importing something or something like this, where it has a checkpoint?
Yeah, it would be fantastic for that. Yeah, yeah.
Oh, wait, but by checkpoint you mean, you're importing the file or whatever,
And you want to
and then
return
it
a partial
stops
thing?
halfway through.
And you want to stop halfway through and then keep going.
Yeah, yeah. No, it'd be great for
Yeah,
that.
I mean, I'm not sure importing import, I think should never do that, but
No. But you
sure.
could
Well,
have
but it's an
files.
alternative to what you do with stream pointers and files and things, which is a total
Yeah.
mess.
For sure, yeah.
But so what would that look like in this generator world where you have instead of writing code that says, F equals, file open and blah, 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 and you get a stream thing, you keep going. What would that look like?
You could, well, I don't know. I mean, it could look like,
You mean like if you wanted an iterator that basically reads files and stuff?
Yeah, but does things,
I mean,
because right now, you read a file and then you make a decision about what to read next. And the state that you're maintaining the state of the file in the stream pointer.
I mean, this is, by the way, this is how, languages like Rust and so on do basically all their I/O.
right,
Okay.
You can have you have yes.
be able to write something to do what you want.
Okay,
And then
so-
of course
so-
you can have functions that potentially apply to this becomes more complicated, but you could imagine something like map that applies to a generator and will, return a new generator that
I understand. That has an
has
F
a function
wrapped
of
around
five.
all the things that it returns.
Yes.
Right.
Well,
Yeah.
This
That's
actually
meta programming with generators in some sense.
Well, this is
yeah.
basically just all the lazy stuff that we talked about a while
Yeah,
ago.
I just wanted to say that in that streaming project that I was developing, there was a lot of these similarities, but this is lower level in the sense that this allows you extreme efficiency without any compromises whenever the code can be compiled.
So could
fully
you
compiled.
write your streaming stuff in using this framework?
Certainly.
Absolutely, I
Well-
think that would be a perfect match. That was the missing part for the. A lot of things I had to do to speed things up was to chunk and vectorize things. Some of those ideas are still valid because chunking is generally a good idea in many cases. But this new addition to the compiler makes a whole lot of use cases tangible, like which wasn't possible before.
Okay,
Right. To be clear, though, this is something I think. Right. Again, there've been several different streaming, lazy, whatever efforts. For stuff that would be like general purpose, top level, implement, iterators and so on, that this doesn't quite help you with, because the fundamental problem is, like in the evaluator, we don't have a way of freezing state and, thawing
Right.
it again.
I understand. So this is only going to be particular for now. It's just particular functions. It's like if we wanted a thing where we have a permutation generator and it's, you run it for a while, you generate a bunch of permutations, then you stop, then you go have a cup of coffee or something, and then come back after you've done a bunch of other computations, and then want to reuse the state of that
Sure.
thing.
In principle, I can do what you wanted, so I can read the things one element at a time, but go back to it if you want to.
Right. But what this is doing, right? This is frozen code state. We've never had a symbolic way to represent code state. We have a symbolic way to represent code, and we have a symbolic way to represent the input and output, but
Right.
we've never had a symbolic way to represent code state.
Which is maybe a shame, but a bit hard to,
Right.
yeah.
Well, when we rewrite the evaluator, we can think about
Sure.
that.
Well, that would be, yeah. We can talk about that as well. But,
Right, but but that's the ultimate thing here, is that what you are doing here is you're representing there's the code, which is an expression, and then there's the running of the code, and this is, we've talked endlessly, and that's what we talked for the multi-computation stuff. We talked about needing to represent the execution history.
right.
Right. This is representing the intermediate state of the running of the code.
Yes. in some low-level LLVME sort of way.
No, I understand, but in principle, and the problem is most code. I mean, let's say we had something like this in the evaluator. We really have no idea how to represent that because the execution state of a piece of code, particularly when you're doing multi-computation, and that it could be some very complicated front of what has been evaluated and what
Right.
hasn't. In this case, there is a single front because it goes in evaluation order, right? There's a single front.
Yes,
There's
yes.
a single yield that has been the most recent one done.
Yes.
Although that's not necessarily, you could imagine a multi-computational version of this where there are multiple parallel yields.
Right.
Yeah,
each
which is
thread could
essentially
yield.
a frozen version of
Right.
our multi-computation story, which we need in the multi-computation case. That is, in the case of an ordinary evaluation, there is an answer, kaboom, or it's
Right.
just still running, right? In the case of multi-computation, there is generally a front of where it's got to and all the threads.
Mhm.
Right, but one distinction is that here it doesn't save any kind of history. It only saves
No, I know.
whatever.
It's
Yeah.
the current state only. I get
Yeah.
it. It's only the front.
It
It's only the
could. I mean, it could do. This is like how
it could
LLVM
save the state, save the history.
it certainly could resave the state, so you could go backwards. This is set up to support C++ coroutines. This is how Clang implements them. So there's lots of cleverness, but in theory, it could go. You could have something where you could have previous, and the function would go backwards if you want.
Yeah.
I mean,
Okay, listen, guys. I
Right.
unfortunately am late for something else, and I really need to go. But I look forward to continuing this. But it seems to me the things that would be worthwhile to think about are a little bit of where does this, are there functions we can build today that are top level functions that live on top of this framework?
I think the answer is yes.
Okay, well, let's figure out what some of those are.
Mhm.
And then there's what the framework looks like, which is, deeply burnt into the data structure world, probably, and somewhat, I don't think, I will be very surprised if we want to have a symbol named something as simple as generator.
Yeah, fine.
Yeah.
That's fine. It was more the collection of not the specific names, but the how many, what the functions are, and
Well,
such
it's
like.
basically
And you want to
generate
have
yield.
another, yeah. And I mean, this is the. Let me just show you. You probably need to head off. This is the sending, thing. So this is kind of like a logger, and this could be quite useful. So now I'm sending thing, but it's in a loop. So this is right, and you have to sort of wake these things up. Should probably instantiate some of these. Right, and so basically I'm sending every expression you send into it, it prints it out, you see.
Yeah, I get it. That's interesting.
And there could be a chain of these things. So you could make quite a nice logger system out of this. So yeah, and so I call next, and so that's triggering the default. Let's change that there. There we go. Right. And so when I call next, it prints the default. Having this default is actually really quite useful. So you want another meeting, Stephen, basically.
I do want another meeting.
Fine.
This is great, but we need a solid hour for this.
Do we think this is a good collection of people? I thought it was not too big, not too small.
I think it's fine. Yeah,
Good.
I think it's a good collection.
Great.
I mean, I think that's but this is going to require. I mean, I really think it will be very worthwhile to think through what some of the early top-level applications of this framework are.
Okay.
And that I think that will help us to make sure we make right design for this low-level stuff.
I'll spend some time on that. Good.
Right. It looks lovely.
Yeah. It's terribly interesting.
It is.
I'm a
I
man
agree,
of,
but I think the multi-computational case
yeah, I'd
is
like to
worth not
understand more about
completely
that.
ignoring.
No. Right.
I mean, Nick is another
I'm
person
not-
we
I'm
might
not
want to Nick the Nick with a
Yep.
K
Yeah,
would be another person to
Sure,
go into
fine.
this.
sounds good.
Okay,
Good,
good stuff. All right.
interesting. Right, okay.